Today we're in Chapter 4 and apportionment problems, and now we get to have Hamilton get involved, Jefferson, Adams, and Webster. We're going to basically be doing the same thing 4 different ways. And now the issue will be, will we remember which method is which? And the answer is probably no. We'll probably have to go looking it up each time. But we're only in this chapter for a little while. So the issue is that the Constitution of the United States says that the House of Representatives will be done in a proportional way. If I have 13 million people in my state and you have 1 million in yours, then I should have 13 more representatives than you do, 13 times as many. The practical issue is we can't have 100,000 representatives. That costs too much money. So we're going to limit the number of representatives to some number. Right now it's 400 and something. And then every 10 years we do a census and figure out how many representatives each state gets. So that's what we're going to do. And there's nothing fair about it. It's just the method that's being used. And so some of these methods are more fair than other methods for the big states. Some of them are more fair than other methods for the little states. There's no right way to do it, and all 4 methods have been done in our history. So that's the way that. But the Founding Fathers left the detail out, and other people had to figure out how to do it. Article 1, Section 2 of the Constitution says that it will be done. And so we'll do it with a kitchen. Mom has 50 identical pieces of candy, and she wants to divide them up among her children as a reward. How is she going to do that for doing the kitchen work? And so now the kids all did that many minutes. It's 900 minutes, and if she has 50 pieces, then I'd probably take that 900 and divide it by 50 and say each 50 pieces should get each 18 minutes should get a piece of candy. Okay, so I have 50 pieces of candy, 90 minutes. So every 18 minutes gets a piece of candy. So I divide 18 into 150 minutes, and I get 8.33. Well, Alan can't have 8.33. That's not going to work very much. That's not going to work out. Is he going to get 8 or is he going to get 9? He can't get 8 1/3. And Betty's supposed to get 4 1/3, and Connie's 9 11/18, and I get 11 1/3, and Ellie gets 16 7/8. And what is Mom going to do? She should probably just eat one, right? That's how it's solved the problem. Give everybody their fair share and eat what's left over. But there has to be some mathematical way to divide up the stuff. So here we are. We're in some Utopia Congress in the year 2525, and we have 1, 2, 3, 4 different regions on my planet, and they're joining into a confederation. We're going to have 50 elders, so we're going to have 50 seats on the planet. So now I touched it again. Went the wrong way twice. All right, so I have different names to protect the innocent, but the same number of things, and I have a population of 900 billion. That was pretty cool. So, and there's 250 seats. How are we going to do a proportionate? How are we going to do that? So we get the population of each state, and this is a total different guy. And we come up with a thing called a standard divisor. So we're going to take the population and divide it by the number of seats we have, or the number of pieces of candy we have, whatever it might be, and we come up with a standard divisor. Every 50,000 people should have a seat. Okay, and then we're going to go and take that standard divisor, and we're going to divide it into each of those numbers to see how many seats they get. We're going to call this the standard quota. So we're going to have a standard divisor, how many people we need per seat, and a standard quota, taking your population, dividing it by the standard divisor, and coming up with what you should be getting. And unfortunately, we're going to end up with odd numbers. So now we have 0.92 and 0.72, 0.08, 0.82, 0.7, 0.76, but we still only have 250, right? So what are we going to do? Are we going to round up? Are we going to round down? Are we going to dodge around? Once we've computed the standard quota and we come up with the standard divisor and the standard quota, then we're going to do something. We're going to say we're going to round down for a fractional of a half and round up otherwise. All right, so now we're going to do that. We did it, and now we have 251 seats. So now that method doesn't work very well. Who is going to be the guy that doesn't get one? Because clearly that won't work. Because we can't afford the 251st guy with his 5 secretaries and 5 admin assistants and desk and office space and everything else. So a conventional rounding of the standard quota is not going to solve the solution. So what are we going to do? We need to come up with a better method, and that's what the rest of the chapter is for. Assigning shifts, assigning gold standards, and lots of things. All right. So the basic concepts. We have seats. Those are whole things. They can't be divided. We have m, identical things, indivisible by some number. That's a whole number. Two of the most important concepts of the chapter is the standard divisor and standard quotas. And once we have them, we're halfway there. Standard divisor, number of people per seat. Standard quota, your population divided by the standard divisor. Now, we have upper and lower quotas. So we have a lower quota is the standard quota rounded down, and the upper quota is the standard quota rounded up. Okay, so I'm going to either round up or round down. So maybe they'll give us something here. Our main goal is to be fair to everybody's concerned. Okay, that will never happen. Okay, done with chapter 1, or section 1. Before we start section 2, let's check homework problems. Okay, so problem number 1, and I have my calculator, so that's good. The Banana Republic is a small country that consists of a populations 1, 2, 3, 4, 5 different places. We have 160 seats in our Congress to be apportioned. We want to find the standard divisor. All right, so problem number 1. We're going to add the population. Three, 3, 1, 0, 0, 0, 0. 2, 6, 7, 0, 0, 0, 0. 133,000,000 969,690,000. And we should probably do that in our head just to say we did, right? Okay, so I have 8 million. So my standard divisor is going to be the population, 8 million, divided by the number of seats I have, which is 160. $50,000. Okay, then I want to find the standard quota for each state. State A, B, C, is there a D? D. Okay, so I take the population, 331,000, divided by 50,000. 2,067,670,000 divided by 50,000. 1,330 divided by 50,000. And 69,000 divided by 50,000. Now we wouldn't necessarily have to write that down. We could just do it on our calculator and forget about writing it, I suppose. 66.2. $53.4. 26.6. 13.8. Okay, so that's my standard quotas for each of the continents, and that makes us done. The next homework problem is 9. The Interplanetary Federation of whatever consists of 6 planets, blah, blah, blah. The Federation is governed by a Congress of 200 seats, apportionment among the planets according to their populations, shown below. The following table gives the planet population as a percentage of the total. Find the standard divisor expressed as a percentage of the total. Okay, so this is number 9. So I have 100% as my total, divided by 200 seats. .5%. So each seat would be 0.5% of the total. Find the standard quota of each planet. Okay, so we're going to have A, B, C, D, E, F, and we're going to go 11.37 divided by 0.5, and 8.07 divided by 0.5, 38.62 divided by 0.5, 14.98 divided by 0.5, 10.42 divided by 0.5, 16.54 divided by 0.5. we can just multiply by 2, right? Dividing by 0.5 is the same as multiplying by 2. 22.74, 16.14, 77.24, 29.86, no, 96, 20.84.
Is that 29.96?
Yeah, no, it's 96. And 33.08. Okay, so now you might want to put those in your calculator to make sure I didn't mess it up too bad. But that I should add these up and get close to 200. 22, 38, 38. Yeah, it looks like I'm getting close to 200. Okay, so that's problem number 9. The next problem is 11, which is in the middle of Hamilton's method. So now we got to go figure out what Hamilton's method is. Okay, so Hamilton's method, which was used in the original Congress, I'm pretty sure, because, let's see, Hamilton. Yeah, he was still alive. He got killed off when Washington was president, I remember, in a duel. Every state gets at least their lowest quota. As many states as possible get their upper quota, with the one with the highest residue, fractional part, having highest priority, first priority, and then so on. All right, so method. Calculate the standard quota. Give each state its lower quota. Give the surplus seats, as many as you have one at a time, to the state with the largest residue, fractional amount, until there's no more surplus seats. Okay, so that's what we're going to do. As promised, we are revisiting the Congress problem we already did, and we're going to do it again. So now here we have our lower quota, and we have 4 extra seats to give away. So the residue, 0.92, gets the first amount. The 0.28 gets the second seat. 0.76 gets the third seat. 0.72 gets the last seat. Then the other 2 guys don't get anything. So the guy with the point, I wouldn't expect the 0.8 guy to get anything, but it looks to me like the 0.7 guy got hosed here pretty bad. The Hamilton's method was used by the United States between 1850 and 1900. And it's also known as Vinton's method or the method of largest remainders. Neither of those things ever show up on a test, so we always call it Hamilton's method. So Hamilton's method, find the standard quotas, give everybody the lowest quota, find out how many seats you have left over, give them the fractional part, the highest guy first. Method is still used today in Costa Rica, Namibia, and Sweden. At first glance, this looks pretty fair. It could be reasonably argued that has a major flaw. And the major flaw is that the residue does not consider the size of the state. So if I had a state with 10 million people and it had a residue of a half, that would mean that it had 5 million people not being represented, basically, and I had another state that only had 1 million people and it had a residue of a half, then that would be 50,000 people not being representative, and if it was 0.1 towards the littler guy, he'd get the quota, and that would make it so it's biased in favor of larger over the smallers. This could be bad, depending on who has the biggest army, I suppose. To be totally fair, Hamilton's method has 2 important things going for it. It's easy to understand, and it satisfies an extremely important requirement for fairness called the Quota Rule. The Quota Rule is going to require that everybody at least gets their minimum quota. So your load, we are going to have a method where there's going to be a lower quota violation and or an upper level violation, and that would be bad. No state should be apportioned a number of seats smaller than its lower quota or larger than its upper quota. And that's our Quota Rule, and I'm sure that will show up someplace on some test sometime. An apportionment measure that guarantees every state will be apportioned either its lower quota or upper quota says to satisfy the Quota Rule. It is not hard to see that the Hamilton method will do that. Right off the bat, this guarantees that there are no lower quota violations. Okay, now we get to work some Hamilton problems. So number 11 is next. Find the apportionment of the Banana Republic Congress as described in exercise 1 under the Hamilton method. Okay, so we'll go back to exercise 1, and we will bring with us the standard quotas that are already calculated. Or A, B, C, D, and we're supposed to have 160 seats. Okay, so we're going to give this guy 66, 53, 26, 13, and we're going to add 66 plus 53 plus 26 plus 13, and we have 158. So we have 2 seats left over. 2 seats. And so now we look for the biggest residue. That guy's got the biggest residue. So he's going to go to 14 seats. And this guy's got the next biggest. He's going to go to 27 seats. So using the Hamilton method, we're going to have 66, 53, 27, 14. Okay, number 21. And number 21 is still in the Hamilton method, and it has to do with candy bars. Am I going fast enough? Don't want to have anybody bored out there. Alright, so we're on live again, looking at number 21. Suppose there's 11 candy bars. Okay, so I got 11 candy bars in a box. Given that Bob did work of 50, okay, so Bob has 54 minutes of work. I don't know what he did, but not relevant. Peter, 243. Ron, 703. How are we going to do the candy bar apportionment using Hamilton's method? All right, well, first of all, we have to figure out what the total minutes are. So total minutes. $703, 243, 54, 1,000 minutes total. So that I'm going to take that and divide it by 11. Divided by 11. And so I have 90.909. And that's probably repeating because my calculator is probably in a three-digit mode. That's my standard divisor. Okay, so now we're going to find the standard quota. I'm going to take 90.909 divided by 54. No, I'm going to go the other way. I'm going to take 54 and divide it by 90.909. I'm going to come up with 0.594. Okay, and then I'm going to take 243, if I could hit the 3 button, and divide it by 90.909.
How did you get the 0.594?
Okay. Okay, so what you're saying is I'm skipping a step. Alright, so I'll put it back in. 54 divided by 90.909. 243 divided by 90.909. 703 divided by 90.909. Okay, so that's what I'm doing. 54 divided by, oh, I already got that one. 0.594. Two 0.673. I don't know that I need that many decimal points, but I got them anyway. .73. Okay, so everybody gets their low quota. 0, 2, 7. 0, 2, 7 is 9 total out of the 11, so I have 2 more. 2 more. So I'm going to give to the highest residue guy, the 0.7, I'm going to add 1 to him. And the next guy is this guy here. I'm going to add 1 to them. And now Bob gets nothing. And Peter and Ron gets 3 and 8. Moms probably don't like that, right?
Right.
A kid not getting anything, I mean, that's not going to work too well. So the B part of the problem probably wants us to correct that. Suppose that before the 11 candy bars are given out, Cousin Jim shows up and he wants to be included in his homework hours, and he has 580 minutes. Okay, to be fair, Mom adds 6 more candy bars, so now she has 17. So now we're going to do part B. Okay, so part B we have we have 54, 243, 703, and 580. And now the number of candy bars we have is 17. All right, so our total, we want a standard divisor, and that's going to be 1,580, because we already know those other guys are all added together to get 1,000, right? Divided by 17. Is 92.94. 92.94. Okay, so we're going to take 54 divided by 92.94, and 243 divided by 92.94, and 703, 92.94, 580, 92.94. And when they get that, we're going to get the standard quota. .581. 2.615. $7.564. 6.241. Okay, so everybody's going to get their low quota 0, 2, 7, 6, which gives us 15, and we have a total of 17, so we have 2 more to give out. All right, so we go looking for the guy with the highest residue, and that's that guy. He's got the highest residue, 0.6 something, so we're going to give him 1. And then the next guy is over here, the highest residue, so we're going to give him 1. And then we're going to end up with 1, 3, 7, 6. And it looks like Ron's not happy because he used to have 8, and now he only has 7. And he's yelling and screaming that this is definitely unfair. And we would explain to him that life is unfair and move on. Okay, the next homework problem is 23, which has... We're done. Oh, there's a C on 21. The results of A and B illustrate one of the paradoxes. Which paradox is this explaining? I have no idea. Any idea? The transparencies didn't have paradoxes in them. It didn't violate the low quota limit or anything. So now we'll have to go look.
New states paradox.
Who?
The answer says new states paradox.
A new states paradox, right. The new states paradox would mean that if I add somebody else to the mix, I shouldn't go down. So yes, I remember that one. Either that or I just made it up. Oh no, I couldn't have made it up.
It's in the book.
Yeah, you had to make it up. Yeah. New state paradox. So the problem was Mom added enough candy, but whoever that first guy was, Bob? Yeah, Bob ended up sneaking one in because of the way we did the residue thingy. All right, so now we're going to go and look and see what Jefferson would do under these situations. Oh, no, we're not. We're going to look at the Alabama and other paradoxes first. All right. The most serious flaw of the Hamilton method is called the Alabama paradox. In essence, it occurs when an increase in the number of seats being apportioned in and of itself forces a state to lose one. Okay, so we go and we add 3 more seats to the Congress, and Iowa loses 1. That would be the Alabama paradox. Obviously, it happened to Alabama. That's why they are calling it the Alabama paradox. So in a country, we have a population of 20,000. We have 200 seats, House of Representatives. And in the Hamilton method, we have quotas that look like that. And now we're going to increase the number of seats to 201. Everything else being equal, and we're going to increase the number of seats to 201, and voila, Bama there gets knocked down. It used to have 10, now they only have 9. So that would be the Alabama paradox. More seats means fewer seats for me. Oh, that's not good. I don't think I like that idea. I like as many seats as I have. Like right now I'm using 1 seat. That should be enough. This is a quirk in the arithmetic. When you increase the number of seats, each state's quota should go and blah, blah, blah. Then we have the population paradox. Sometimes in the early 1900s, it was discovered that under the Hamilton's method, a state could potentially lose some seats because its population is too big. This is called the population paradox. To be more precise, it occurs when State A loses a seat to State B, even though the population of A grew at a higher rate than the population of B. Too weird? Probably. So 2025, we're on Utopia, and we're doing 50 seats are being proportioned, and there they are, and they're all proportioned, everybody's fine, and we're going to do it again, but we have more population. A tale of 2 planets. All right, well, we'll just believe that it's going to work. So we have 2 planets, blah, blah, blah. We're adding some planets, and under the Hamilton method, it looks like we went up, and they were given to somebody else. Notice the total population increased to 9.9 billion. Standard divisor changed, and Ellison lost a seat. Oh, well, that's fine. Hamilton method has a population paradox. So this is 1907. Oklahoma joined the Union. Prior to becoming a state, there were 386 seats in the House of Representatives. Time for fair proportionate, Oklahoma would get 5, so the size went up 5 more. The point of adding these 5 seats was to give them to Oklahoma, would be their fair share, and leave the appropriation of the other seats unchanged. Unfortunately, that's not what happened. New York went down. Boy, did New York not like that. And if you recall, the President of the United States at the time was what's his name? Roosevelt, Teddy Roosevelt, from New York. And he had a big mouth, right? And he carried a gun. And so that caused a problem. So now we have a garbage time. Metro Garbage Company has a contract to provide garbage collection to some homes. We're going to do a standard divisor 1,000 homes. And we're going to decide whether the north-south or the south side of town gets a number of garbage collectors, and the north side gets 10, and the south guys get 90. That seems fair, doesn't it? And but now Newtown comes in with 5,250 homes. We do it again, and now Northtown goes up by 1, and Southtown goes down by 1, and Newton gets the 5 they're supposed to. That doesn't seem right. I don't have enough garbage men. There are 2 key lessons we should take from this. In terms of fairness, Hamilton's method leaves a lot to be desired, and the critical flaw in the method is the way we handle the surplus seats. Clearly, we have to find a better way. All right, well, now that we've talked to you about that, now I can move away from this and go to the next section. And that would be 4. And better way is a better way to translate that is a more difficult mathematical way, right? Because that way was pretty simple. I liked it. Even I could do it. Jefferson's method was Jefferson was okay. Jefferson method is based on different from Hamilton's. It is the handling of the surplus seat that Hamilton's method run into trouble. So here's an interesting idea. Let's tweak things so that when the quotas are round down, there are no surplus seats. The answer is changing the divisor, which when changes the quotas, the idea is that using a smaller divisor will make a bigger quotas bigger, and so that's what we're going to do. So we're going to go in. Our first standard divisor is 5,000. We get to the standard quotas. We have too many, so we change the standard divisor by a little bit, and then we do it again. So here we go. The first time we have 246 seats given out. Instead of taking the 4 extra and giving them away, we drop the standard divisor by a little bit. How much do we drop it by? Well, in this case 500, but you could drop it by 1 and do it, and 2 by do it, and 3 by do it, but clearly they did it by 500 and got the right answer, so that's the right thing to do. So it looks like maybe 0.1% or so, so some small amount, and now you end up with no leftover seats. Now who got, B got 2 seats, and A got 1, and D got 1. So this is going to violate the no one gets more than their upper limit rule, right? There's nothing short of magic. Of course, there's you are wondering, where did we get that from? And it's called a lucky guess. And that's our calculators work pretty fast, so it wouldn't take too long. So now we're going to do it again. We're changing the divisor, is what we're doing. Jefferson Method. Find a suitable divisor that'll work. Use that divisor to compute the state quotas until we get to the lower quota is everybody. I can almost remember that one too. How does one find a suitable divisor? There are different ways. Educated guess, trial and error. Okay, finding D. Make an educated guess, choose a divisor. If it works, you're done. If it doesn't, go either up or down depending on what you need to do. Oh, there we go, flowchart. We find the standard divisor someplace. Yeah. So we found the standard divisor. We go and pick a number shorter than that. If it works, we're done. If it doesn't work, then we either increase it or decrease it to make it work. Is that complicated enough? For the computer science majors, we have to have flowcharts, right? Yeah. The first guess should be the standard divisor should be smaller than what you had before. And shouldn't take any more than a couple guesses. By design, Jefferson's method is consistent in its approach to apportionment. The same formula applies for every state. By doing this, Jefferson's method is able to avoid the major flaws of Hamilton. There are, however, problems with this method, and the problem is you could produce a upper quota violation, and no one's going to like that. All right, time to do homework problems on the Jefferson method. 23. Number 23. Find the apportionment of the Banana Republic guy again in exercise 1 using the Jefferson method. Okay, so we'll go back and get the results. And we're going to come back and get that many results.
We have to rewrite all of that out, or can we just write the decimal numbers out?
Copy. You just write the decimal numbers out. Yeah, I tell my adjunct instructor whatever he does is right. Okay, now as I recall, we didn't have enough, right? We're too shy. Yeah, 160, and I think that's 158. 66 plus 53 plus 26 plus 13. Yeah, 158. So what we're going to do is we're going to come up with a new standard divisor, and because the book only went down by 500, we're going to go down by 500. So we're going to have a new divisor, 49,500. And we're going to take 3310 divided by 49.5. I'm dropping zeros. 2670, 49.5. 1330, 49.5. 690 divided by 50, 49, 49.5. Okay. Is it okay if I drop the other zeros? Too late, I already did it.
It's gotta inform us what you're doing.
Yeah, well, it's a mystery. 66.8. I'm saving ink. Yeah. 53.9. 26.8. 13.9, and I didn't make it. I'm exactly where I was before. Now, I'm pushing closer. I went from 0.2 to 0.8, 0.4 to 0.9, 0.6 to 0.8, 0.8 to 0.9, but I'm not there yet. And now, if I go up by another 500, if I go down by another 500, I'm probably going to push him, and all of them over. I'm going to be over, right? So we're going to have to be smarter than the average calculator here. So we're gonna pick a new guy, and I'm going to pick 49,400. Okay, so I'm going to go 3310, 49.4, 2670, 49.4, 1330, 49.4, 690, 49.4, because we only want the two guys that are 0.9 to go over is all that we want. 3310. Bummer. 67. Bummer. 54. The other two can't go over. If they do, that won't work. 20. Oh, good. 26.9. That's good. 13.9. So we're there. So I'm pretty sure that 67 plus 54
That's 13.9 is
plus,
what you said.
yeah, it's 13.9. So the lower limit is 13. So that makes 160. Yeah, this is a 0.9. These had points in it too, but we're going to drop the points anyway, right?
Mm-hmm.
So we got it in two guess. 31. Suppose that you just took a test on this chapter. One of the questions on the test was to calculate the Texas apportionment of the House of Representatives would be for the 2000 census taken under Jefferson's method. Your friend claims that he did all the calculations and got an answer of 31. It's immediately clear to you that your friend's answer was wrong. Explain how you know. Do exercise 7 first. Okay, So we're doing number 31. Well, I can answer the question without doing exercise. Well, that wouldn't be good, would it?
Works for me.
Well, what's the only way that you'd immediately know the answer was wrong?
I don't know.
Well, if there was a lower limit violation, lower limit violation. Because by this method, you could never be less than the lower limit. Because all you're doing is you're changing the divisor until you creep the guys up a little bit to get them higher. But if anybody went lower than the lower limit, then you know it was wrong. So if we went to the exercise 7 and we did it, we would see that 31 is lower than its lower limit, and therefore a lower quota. Therefore, we'd immediately know that. Any other method we wouldn't know unless he was 5 away or 6 away. Then that'd be easy, right? But I'm pretty sure that's what we're doing. Okay, it looks like we're done with Jefferson. Now we're moving to our glorious pal.
Are we just going through the whole chapter then tonight?
We could. That could happen. Unless these problems get extremely hard real quick. All right, so Adams. All right, like Jefferson, Adams' method is also a divisor method. We're gonna change the divisor, but instead of rounding it down, we're gonna round it up. For this to work, the modified quotas have to be made smaller, and this requires the use of a larger divisor. Okay, so I'm going to round it up. 1, find a suitable divisor. Using that in divisor, compute the state's modified quota, and now we're going to use the upper limit. So we're going to use the upper quota instead of using the lower quota. So we're going to make D bigger than the standard quota, and we're going to pick the upper quota as what we do. Okay, so this is back to Paradox's Congress. So the first time through, we have 102,000 using the upper quota. We end up with 251. We raise the quota by a little bit, and B loses 1 person, and now we're at 250, and we're there. Right? So in Adams' method, we're going to the upper limit, the upper quota, and then we're changing the divisor so that we get the right number. Okay. Well, that was quick. All right. So now we're looking at 33.
Last ball hit paste.
Number 30. Can I do that?
Yeah.
Edit.
Because all your information's still there. You haven't copied
Paste.
anything.
Okay, I haven't copied anything else. Okay. So there we go. So this is 33. Find the apportionment using the Adams method. All right, so using the Adams method, we would have 66. No, the upper guy. 67. 67, 54, 27, 14. 67, 67 plus 54 plus 27 plus 14. So we're 2 over. So we're 2 over. So we're going to pick a D that's going to be higher. Okay, so if we can get rid of that guy and this guy, that would be good. So we're going to pick 5,300. Okay, 5,300. And we're going to go with 3310 divided by 50.3, 2670, 50.3, 1330, 50.3, 690, 50.3, and because we're going to take the upper quota, we're going to round up on all of them and only put that number down, 3310, 50.3, and that's going to be a 66. 2670 divided by 50.3. That's going to be a 53. 1330 divided by 50.3. 26. 27. 66 is right, but this is not 63. This is 64.
54.
Yeah, 54. Well, I went the wrong way. That's 27, so that's right. 690 divided by 50.3 is 20. 690 divided by 50.3, 14. Okay, so now we're 1 over. Okay, so we're still 1 over. So we're going to change our divisor. And we're going to change it to 50.4. 3310, 50.4. 66. 2670, 50.4. 53. 1330, 50.4. 27. 690, 50.4. 14. And now we have the right 160, and everybody's happy. Is that really 160? Yeah, it must be.
60, 80, 90, 9,
Yep. So we're there. We made it. All right, so that was number.
That was number 33.
33. All right. Okay, 41's next. Under Adams' method, California's apportionment is, in 2000, was given 50 seats, even though California's standard quota is that. What does this fact illustrate about the Adams' method? It illustrates that it violates the lower quota rule. Yeah, that's good enough. All right. Oh, now we're on to Webster. Now Webster had better be more difficult than these other guys, otherwise we may have to go home early. No, don't count on that. Okay, Webster, there we go, Webster. I didn't see how many things it is. What is obvious, the promise between rounding the quotas, either up or down, blah, blah, blah. Now, we can use a modified divisor to manipulate the quotas it's very possible to find a suitable divisor that will make conventional rounding work. All right, so we're going to find a suitable divisor. We're going to use that suitable divisor to compute each state's standard quota, modified quota. Then we're going to find an apportionment by rounding each modified quota in the conventional way. Okay, so we're gonna change the standard divisor and then either round up or round down, depending on whether or not you're greater than 0.5, and then or less than 0.5. And then if we have the right number, we're going to say it's right. All right. So here we use the standard divisor of that. We got 251 using the nearest integer. So that guy's 33. He got rounded up, rounded up, rounded down, rounded up, rounded up, rounded up. And then we change the standard divisor by a little bit. And then we round up, we round down, we round down, we round up, round up, and we get 250 and we're there. Okay. So that's the Webster's method. Now Webster, I think, was actually used once. Forget when. Flowchart illustrates how to find a usable divisor, blah, blah, blah. So we start with a standard divisor. We round up and down. We decide whether or not we have to make the divisor bigger or smaller to make it work. And then we do it. Webster's method tends to produce apportionments that don't stray too far away from their standard quotas, although occasionally we do have violations of both upper and lower quota rules, but such violations are rare. Real-life apportionments are possible. Webster's method has a lot going for it. It does not suffer for any of the paradoxes shown by the other methods, and it shows no bias between large and small states. And it was actually used to proportion the House of Representatives 1842, 1901, 1911, 1931, until it was replaced by another method that's so complicated that there's no way it's going to be covered in this chapter. Aren't we lucky? I don't even know what that method is, but it's probably just plain guess. It's probably all I know. Okay, so now we have 2 more homework problems. Yes. So 43, and we'll follow the same method we did last time of saying edit, paste. All right, so that's what we have. And if we were to round up or down in the conventional way, we'd get a 66, a 54, a 26, and a 13. And we have minus 2 seats. So we need to get 2 more.
Okay, I'm confused.
We're going to round in the conventional way. So that's a 0.2, we round to 66.
Okay.
0.4, well, yeah, I'd be confused too. That's what you're confused about that right there?
And then, so 26 needs to go to 27.
That makes 2 in a row.
That would be why I was getting confused.
You're pretty confused. How could you be that confused? I mean, really?
Sheesh.
And you're in the front row, too. All right, so this is a 3, that's a 7, this is a 4. I better have another sip of my Coke, otherwise we won't be able to work this problem.
I agree.
So now I got to figure out how many seats I gave away. 66 plus 54 plus 27 plus 14. I got the right number. I don't have to do.
53.
Huh?
53, not 54.
Oh, I'm sorry. I put in 53.
Did you?
Yeah. 66 plus 53 plus 27
That'd be right.
plus 14.
Then those are the right answers. 66, 53, 27,
So-
14.
So I'm already there.
Awesome.
Find the apportionment using the Webster method, and we're done already. Way to go, author. Hey, you're my pal. All right. 43. I just did 43.
Yep, 43 is done.
53 is next. That's really a lousy. I better change the problem set because that was really bad. I can't round up or down properly, but other than that, everything's fine. Consider the problem of proportioning 3 seats between 2 states using the Jefferson Method. Let PA and PB denote the populations of A and B, respectively. Show that if the apportionment under Jefferson's method gives all 3 seats to A and none to B, then more than 75% of the population must be in A. Okay. All right, so Jefferson's method. Okay, so we're going to, Jefferson's method, we use the lower quota, and we change the divisor until the lower quota is our limit. Okay, so that's what we're going to do. Okay, so we have a standard divisor. The standard divisor is population A plus population B divided by 3. Okay. And we're supposed to show that if the apportionment under Jefferson's method gives all 3 seats to A, then more than 75% of the population must be there. Okay, so I got to show we have PA is going to be greater than 3 times PB. Okay, so that's going to be the case. All right. This looks like a math problem. Is this a math class? Who assigned this as homework anyway? Who was that guy? Don't be looking in the back now. There's probably nothing back there to help anyway.
No, it's just all words.
Okay. So my standard quota is going to be PA divided by PA plus PB over 3. And it's going to be PB over PA plus PB over 3. Okay, so that's my standard quota. Now, I'm going to go with the lower limit. Okay. And I'm going to say that A has 3 and this one has 0. Okay. So PA divided by PA plus PB over 3 has to equal 3, the lower limit, 3 point something, Okay, so I'm going to say that this has to be greater than 3. Okay, so that number has to be greater than 3 so that when we go to the low limit, I end up with 3. Okay. So now I'm gonna cross multiply and say PA is greater than PA plus PB. Because I have 3 over 3, they're going to go away. 2PA is going to be greater than PB. Now I went the wrong way. Why did I go the wrong way? Three divided by I cross multiply, I get that. I get 0 is less than PB. That's not what I'm looking for, though. That's not going to help me. PB is less than 0. Okay, we're going to go, we look over on this side, that means that this number has to be less than 1. Okay, if that number is less than 1, then PB has to be less than PA plus PB divided by 3. Okay, so if I go in and put the 3 over there, 3PB is less than PA plus PB. 2PB is less than PA. But we want it to be 3PB. How come I have 2PB? 2. Okay, so it must be over here someplace. PB. Oh, I got an idea. Why don't we see if I have the solution guide? What do you think about that? Is that called? That's called It's Not There. Oh, as I was saying.
Are you going to put that on Angel?
The whole solution guide?
Yeah.
Oh, that'd be a waste of time. What problem is this? 53?
Oh, well,
That's exactly what the back of the book says.
If the modified divisor for D, oh, we have to do it by the modified divisor, gives us more than 3. That's B, blah, 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 blah. Okay, well, that's exactly what the back of the book says.
Yeah, pretty much.
All right, well, we'll just go with that and then not worry about it.
So are we just
No, we have 2 quizzes to do.